Okay, so I recently had somebody on the web reach out to me and ask me to show how we could use a minimization solver and optimization solver to solve a geometric constraints problem. So in this particular case, somebody asked me to look at this particular case. We have 3 points. Point 1, P1 has an x-coordinate and a y-coordinate. Point 2 has an x-coordinate and a y-coordinate, and point 3 has an x-coordinate and a y-coordinate. We're just looking at two-dimensional space. This would be useful for example solving sketches when using parametric CAD systems. So each of these 3 points are defined by a few constraints. One of them is this distance constraint, which is this is the equation of a circle, stating that P1 and P2 are 200 units away from each other, P2 and P3 are 300 units away from each other, and P1 and P3 are 250 units away from each other. Additionally, we have a constraint that P1 is fixed at units 100, 100, and also that points P1 and 2 are horizontal, or in other words, that their y constraints are the same. So what I'm going to go ahead and do is I'm going to go ahead and write out these 3 constraints. So F1, F2, and F3. And I'm going to go ahead and fill out the equations for this. So this first one is P2x. So we'll go up here and get P2x minus P1x, that quantity squared. Oops, somehow that got messed up. Plus P2y minus P1y, quantity squared, minus 200 squared. Okay, so there's our first constraint equation. Second constraint equation is going to be equal to the quantity P3x minus quantity P2x squared plus P3y minus P2y squared. Didn't quite finish that one up. Minus 300 squared. Okay, and then the last one is going to be P3x minus P1x. Oops. This quantity squared plus P3y minus P1y squared minus 250 squared. Okay, so we have these 3 constraint equations. We know that from the additional constraints here that P1 is fixed at units 100 and 100. Additionally, that P2 and P3, or P1 and P2 are horizontal. So I'll go ahead and take the y coordinate for P2 and make it equal to the P1 coordinate. Okay, right, and we're just going to make some guess over here at these other ones. Let's maybe call it like 500, 500, 500. Okay, now what we need to do is, if we're going to use an optimization method, we need to combine these constraints into a single equation which needs to be minimized. So ultimately we want to find the roots of these equations, or in other words where they truly are equal to 0. We're going to manipulate P1y, P2x, and P2x, P3x, and P3y in order to get all of these equations to be true. So this is an exactly constrained system. There's only one well, there are true answers that are exactly correct. It's not under-constrained, meaning if you're making a sketch, you could still drag the things around. There actually are multiple answers to this. There are multiple roots to this, one in the positive coordinates and one in the negative coordinates. But anyhow, let's go ahead and we're going to create big F, which is going to be equal to this quantity squared, so the constraint from the first equation plus the second one. I'm sorry, I've got some problems with my keyboard here. Plus the third one squared. Each one of these quantities squared because we're trying to find their roots. Okay, now we're going to go ahead and use the GRG solver optimization routine that's built into Microsoft Excel. This is a fantastically good solver. And first off, you have to make sure it's enabled. So go up here to File and go down to Options and go to Add-ins. And go down at the bottom, it says Manage Excel Add-ins. We'll go ahead and hit Go. Make sure that you have the solver add-in checked. I believe you usually have to restart after that, but I can't quite remember. Let's do one other thing. We need to do some color coding here. These two variables are constrained. We're not going to be changing them, as well as this one. Those were all defined by the fact that we knew that P1 was at 100, 100, and that P1 and P2 were horizontal. Okay, so the rest of these are the variables that we're going to be adjusting to optimize the result, or to get the result hopefully to be 0. Okay, so to use the solver, you'll go up here to the top ribbon, go to Data, over here to Solver, and set the objective. This is our summed up formula here. This is the thing we're trying to minimize. We're going to go ahead and set it to a minimum. And by changing which variable cells, we'll go ahead and select these 3 cells that we've defined as these cells that can change. We're going to go ahead and I'm going to go ahead and uncheck this, and we're going to use the GRG nonlinear solver, and we'll go ahead and hit solve. And this was an unexpected result. Give me just a second, and I'm sure I made a typo. Let me find it. Okay, so I found the problem here. I made a typo here indeed. This quantity should have been squared. I cubed it in the equation. Okay, I'll go back to the solver and run the solver again. Once again, we're trying to minimize some of the squared errors by changing these variables that we're interested in. So we'll go ahead and hit solve, and here we go. So here the coordinates of P2x are 300, P3x is 131.24, and P3y is 348. Okay, those numbers are not exactly perfect. That has to do with the options that were used in the method. So if we look at constraint precision, let's go ahead and find GRG nonlinear. We're going to use central derivatives instead, and we'll use a convergence. We're going to have about 2 more zeros in there. It'll require this algorithm to go a little bit further. And okay, there we go. That's a little bit better. Now this is 300, 131.25, and then 348.039. So this has used the optimization routine, GRG optimization routine, to solve this really system of nonlinear constraints to find the correct coordinates for this geometric constraint problem. I've previously used the BFGS method in SketchSolve, and that works just fine. It's not as good of an algorithm as the GRG method is. I frankly would have used the GRG method if I knew it and if it were available to be used in a piece of software like SketchSolve. BFGS method or many of the other optimization methods would have been very much similar, with the exception that they would solve the problem slightly differently. It may take fewer or more iterations to solve the problem. Now, an interesting point here, I said earlier that there is at least one more position. I think there's actually 2 more positions that are possible to solve this system of equations. Let's go ahead and make something like negative 150, negative 150, negative 150. Let's go ahead and solve this again. And we'll see, hey, there's another position, negative 168.7 and negative 148, that also is a valid solution to this system of constraints. This is why initial conditions are so important in solving these equations, especially when we're using a sketch for a piece of CAD software or something like that. it's important that we have good initial conditions. This is usually captured because typically when you're sketching a sketch with those constraints, you have design intent and you place things close to where they're going to be. So it's usually unlikely that your optimization routine would jump to one of these other solutions. But keep in mind, as we get more constraints and more variables, there are many possible solutions to a constraint problem. And we hope that we get the right one based off of initial conditions, and also some of the really good geometric constraint solvers out there also use a lot of heuristic rules to attempt to not flip over a sketch into a different position. So that's all.